This is a summary of what we did in class on Monday, September 14th. We looked at cylinders and quadric surfaces. This PowerPoint is in the Unit 2 module, so if you want to look at it on your own at your leisure, you can certainly do that also. First, we remembered just conic sections in 2 dimensions. Circles have equation x squared plus y squared equals r squared. Ellipses, similar, although the coefficients of x and y may be different. Parabola, one of the variables is squared and one isn't. And hyperbolas, we had a difference rather than a sum. Looks similar to an ellipse. But it's a difference rather than a sum. So those are what we had, conic sections in 2 dimensions. In 3 dimensions, if I have 2 variables only, I don't get just a curve, I get a cylinder. We're used to circular cylinders like these. All 3 of these are circular cylinders where the cross sections are circles. The top one, z can be anything because it's not in the equation. So symmetry is with the z-axis. And the second one, x can be anything. And in the third one, y can be anything. We can have a cylinder based on any curve. So we have a parabolic cylinder and a sinusoidal cylinder. We can have a logarithmic cylinder, any kind of curve. Extends forever. When we talk about quadratic equations in 3 dimensions, we get surfaces, quadric surfaces. Not all of these terms are present in every equation. Our goal is going to be to recognize these quadric surfaces from their equations, just like you recognize y equals x squared as a parabola in 2 dimensions. We want to recognize these quadric surfaces from their equations. We're going to look at them by looking at cross sections or traces parallel to each of the 3 coordinate planes. These cross mixed terms rotate the axes, same as they do in 2 dimensions. We're not so much concerned with those, but just so you're aware, that's what those do. This looks very much like the equation of the circle. If we hold z constant, so z squared over c squared is a constant, I'm going to move it over to the other side with the 1, and I have x squared over a squared plus y squared over b squared equals some constant, big K. Well, if I graph just those 2 dimensions, here's x, here's y, I get an ellipse. So cross sections parallel to the xy plane in this shape are ellipses. Notice if you hold y constant and if you hold x constant, we also get ellipses parallel to the other 2 sets of planes. So this produces an ellipsoid. Just like a circle is a special case of an ellipse, a sphere is a special case of an ellipsoid where a, b, and c are all equal. What if one of my variables isn't squared? So here my z is not squared. If I keep z constant, I have x squared plus y squared equals a constant, so I get ellipses parallel to the xy plane. If I keep y constant, I have some version of z equals x squared, which is a parabola. So in the xz plane, parallel to the xz plane, I have parabolas. Same thing parallel to the yz plane. I have z equals y squared. Parabola is parallel to the yz plane. If I put all 3 of those dimensions together, I get a paraboloid. The non-squared variable indicates the axis. So here, the axis of symmetry is the z-axis. If I want paraboloid whose axis of symmetry is the y-axis, then I'll have y as the not squared variable, like that. More variations on this theme of quadratic equations. This time, this looks similar to a paraboloid, except for I have minus instead of plus, which means if I hold z constant, I'm going to have some version of constant equals x squared minus y squared, which is a hyperbola with the x-axis as its axis. Anytime you're drawing traces, make sure you label the axes. If we're drawing 2 out of 3 dimensions, I got to know which 2 they are. So in one direction, I'm going to have hyperbolas. In the other 2 directions, let's see, parallel to the xz plane holding y constant, I have some version of z equals x squared. Those are parabolas. And if I hold x constant, I have z equals negative y squared, which are parabolas pointing down. Sorry, this is not x, this is y, z. When I put all of those 3 dimensions together, this is the exciting one. I get a hyperbolic paraboloid, or kind of a saddle shape. And we can see here's parabolas going down, here's parabolas going up in this direction, and then my hyperbolas are kind of going in towards each other on the sides there. Z squared equals x squared plus y squared. In one direction I get hyperbolas, or actually in 2 directions I get hyperbolas, and in the other direction I get ellipses. You can play around with a little bit of algebra there and convince yourself of that. When I put all of that together, I have a cone. The one that's by itself tells the axis. So z squared by itself, I'm symmetric around the z-axis. Suppose this almost looks like an ellipsoid, except for one of my terms is negative. Well, when one of my terms is negative, I'm gonna again get some hyperbolas. I have ellipses in the parallel to the xy plane, and hyperbolas in the other 2 directions. Since they're ellipses, I'm not going to have an open figure like I did with the saddle, but instead we're going to get a hyperboloid of one sheet. So hyperbolas in front of you and behind you, and ellipses going around this way. Here we can tell what the axis of symmetry is by which variable is negative. So the z-axis, if I change which one is negative, I change the symmetry. What if I have 2 negative terms? Well, if I have 2 negative terms, now I'm going to get hyperbolas in 2 directions. If I keep the z term in either of the other 2, that's going to give me hyperbolas. If I keep z constant, I have negative x squared minus y squared equals 1. Well, what if I multiply through? I got x squared plus y squared equals negative 1, and then plus whatever constant z is. So this might be fine if k is big enough to make the right-hand side positive, and it might not be fine if k is smaller. I might have x squared plus y squared equals something negative, which certainly can't happen. Here's the result. A hyperboloid of 2 sheets. So the space in the middle is what happens if my value of z is not big enough to make up for the -1. I get an impossibility in the middle there. And otherwise I have hyperbolas and ellipses.